Welcome to Cosmic Pulse, where we feel the pulse of the universe. I'm your host, and today we're embarking on an incredible journey into the most mysterious and awe-inspiring objects in space: black holes. Imagine a place where gravity is so powerful that not even light, the fastest thing in the universe, can escape its grasp. A place where time itself warps, slows down, and maybe even stops. That's the enigma of a black hole, and it's been captivating scientists, astronomers, and dreamers for over a century. Did you know that the first ever image of a black hole was captured just a few years ago, in 2019, showing us a glowing ring of light around a dark void? That was just the beginning. In this 1-hour deep dive, we're going to explore everything about black holes: what they are, how they form, the incredible ways we detect them, and the mind-blowing discoveries that have come to light in 2025 so far. We'll also look at how black holes shape galaxies, bend time and space, and what the future holds for studying these cosmic giants. Whether you're a space enthusiast or just curious about the universe, this video is for you. So buckle up for a cosmic ride through the unknown, and if you enjoy this journey, don't forget to hit that like button, share with a friend, and subscribe to Cosmic Pulse for more space adventures. Let's get started. Let's start with the basics. What exactly is a black hole? To understand this, we need to think about the life cycle of a star. Stars are born in massive clouds of gas and dust, called nebulae, where gravity pulls particles together until they ignite in a fiery process called nuclear fusion. This fusion powers the star, creating elements like hydrogen and helium, and keeping it stable by pushing outward against gravity's inward pull. Our Sun, for example, has been doing this for about 4.6 billion years. But what happens when a star runs out of fuel? For a star like our Sun, it'll eventually become a white dwarf, a small, dense remnant. However, for stars much larger, say 20 times the mass of our Sun or more, the story is far more dramatic. When these massive stars exhaust their fuel, they can no longer resist gravity's relentless pull. The core collapses under its own weight in a catastrophic explosion called a supernova. This explosion is so powerful that it outshines entire galaxies for a brief moment, scattering elements like carbon, oxygen, and iron into space, the very elements that make up life as we know it. But what's left behind after the explosion is even more fascinating. The core of the star, now incredibly dense, collapses into a point of infinite density called a singularity. This singularity is so dense that it warps the fabric of space-time around it, creating a region where gravity is so strong that nothing, not even light, can escape. That region is what we call a black hole. Surrounding the singularity is a boundary called the event horizon. Think of it as the point of no return. Once anything crosses this invisible line, it's gone forever, swallowed by the black hole. There are different types of black holes too. Stellar mass black holes form from those massive stars and can be 5 to 100 times the mass of our Sun. Supermassive black holes, on the other hand, are millions or even billions of times the Sun's mass, and we'll talk more about them later. There are also theoretical primordial black holes, which might have formed in the early universe, and intermediate mass black holes, which bridge the gap between stellar and supermassive ones. Each type has its own mysteries, but they all share that defining trait: a gravitational pull so intense that they bend the rules of physics as we know them. The concept of black holes might seem like something out of science fiction, but it actually dates back over a century, rooted in some of the most groundbreaking theories in physics. Let's go back to 1915, when Albert Einstein published his theory of general relativity. This theory revolutionized our understanding of gravity, describing it not as a force, but as a curvature of space-time caused by mass and energy. Massive objects, like the Sun or Earth, bend space-time around them, And that's why planets orbit the Sun. It's following the curves in space-time. Einstein's equations were complex, but they predicted something extraordinary. If an object were dense enough, it could curve space-time so much that light itself couldn't escape. At the time, this idea was more theoretical than practical, and Einstein himself wasn't sure such objects could exist in reality. But just a year later, in 1916, a German astronomer named Karl Schwarzschild found a solution to Einstein's equations that described exactly this kind of object, a region of space-time where gravity was so intense that nothing could escape. This solution introduced the concept of the event horizon and what we now call a black hole, though the term black hole wouldn't be coined until much later. For decades, black holes remained a mathematical curiosity, with many scientists skeptical they could form in nature. That changed in the 1960s and 70s, thanks to the work of physicists like John Wheeler, who popularized the term black hole, and Stephen Hawking. In 1974, Hawking made a groundbreaking discovery. Black holes aren't completely black after all. He showed that due to quantum effects near the event horizon, black holes can emit radiation, now called Hawking radiation. This means black holes can slowly lose mass and energy over time, potentially evaporating entirely after billions or trillions of years. Hawking's work bridged general relativity and quantum mechanics, two fields that don't normally play well together, and it opened up new questions about the nature of black holes. Fast forward to 2019, and the Event Horizon Telescope gave us the first direct visual evidence of a black hole. This international collaboration used a network of radio telescopes around the world to capture an image of the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The image showed a dark shadow surrounded by a glowing ring of hot gas, the light being bent by the black hole's gravity. It was a historic moment, proving that black holes weren't just theoretical, they were real, and we could see them. 2025 has been an incredible year for black hole research, pushing the boundaries of what we thought we knew. One of the biggest breakthroughs has come from gravitational wave detectors like LIGO and Virgo. These observatories have spotted more black hole mergers than ever before, giving us a clearer picture of how black holes grow and evolve. For example, a recent merger detected in early 2025 involved two black holes of unequal sizes, one about 50 solar masses and the other just 10, creating a new black hole with a unique spin pattern. This kind of data helps scientists test theories of gravity and understand the dynamics of black hole collisions. Another exciting area of research is primordial black holes. These hypothetical black holes, which might have formed in the chaotic conditions of the early universe, have long been considered a possible candidate for dark matter, the mysterious substance that makes up about 27% of the universe's mass. In 2025, new theoretical models have suggested that primordial black holes could explain some of the gravitational wave signals we've detected, especially those that don't match the expected patterns of stellar mass black holes. If true, this could be a game-changer for cosmology, offering a new way to understand dark matter and the early universe. On the theoretical side, scientists have made strides in connecting black holes to quantum gravity, a field that tries to merge quantum mechanics with general relativity. One study published in 2025 proposed that black holes might act as quantum computers of sorts, storing and processing information in ways we don't yet fully understand. This ties into the famous black hole information paradox, which asks what happens to information that falls into a black hole. Does it disappear, or is it somehow preserved? These new models suggest that black holes might hold the key to unlocking the mysteries of quantum gravity potentially leading to a unified theory of physics. And let's not forget the ongoing work with the Event Horizon Telescope. In 2025, the EHT has been refining its techniques, aiming to capture even clearer images of black holes like Sagittarius A and M87, with hopes of studying their magnetic fields and how they launch those powerful jets. Now let's talk about the giants of the black hole world, supermassive black holes. These monsters lurk at the centers of nearly every galaxy, including our own Milky Way, and they range from millions to billions of times the mass of our Sun. The one at the heart of the Milky Way is called Sagittarius A, and it's about 4 million solar masses packed into a region smaller than our solar system. How do we know it's there? For years, astronomers watched stars near the galactic center moving at incredible speeds, some as fast as 3 million miles per hour. The only thing that could explain those orbits was a massive, invisible object with immense gravity, a supermassive black hole. In 2022, the Event Horizon Telescope confirmed this by capturing an image of Sagittarius A, showing the same kind of glowing ring and dark shadow we saw in M87, though it was much harder to image because of gas and dust in the way. Supermassive black holes play a crucial role in shaping galaxies. As they pull in gas and stars, they create accretion disks that heat up and glow, sometimes outshining the entire galaxy. Supermassive black holes can power active galactic nuclei or quasars, which are so powerful that they shoot out jets of plasma at nearly the speed of light, stretching thousands of light-years into space. These jets can influence star formation by heating up gas or clearing it away, essentially acting like cosmic regulators. But how did these supermassive black holes get so big in the first place? That's still a mystery. One theory is that they started as smaller black holes, maybe from the first stars that formed after the Big Bang, and grew by merging with other black holes or gobbling up huge amounts of gas. Another idea is that they formed directly from massive clouds of gas in the early universe, collapsing into seed black holes that then grew over billions of years. Whatever their origins, supermassive black holes are key to understanding how galaxies evolve, and they continue to surprise us with their power and influence. 2025 has been an incredible year for black hole research, pushing the boundaries of what we thought we knew. One of the biggest breakthroughs has come from gravitational wave detectors like LIGO and Virgo. These observatories have spotted more black hole mergers than ever before, giving us a clearer picture of how black holes grow and evolve. For example, a recent merger detected in early 2025 involved two black holes of unequal sizes, one about 50 solar masses and the other just 10, creating a new black hole with a unique spin pattern. This kind of data helps scientists test theories of gravity and understand the dynamics of black hole collisions. Another exciting area of research is primordial black holes. These hypothetical black holes, which might have formed in the chaotic conditions of the early universe, have long been considered a possible candidate for dark matter, the mysterious substance that makes up about 27% of the universe's mass. In 2025, new theoretical models have suggested that primordial black holes could explain some of the gravitational wave signals we've detected, especially those that don't match the expected patterns of stellar mass black holes. If true, this could be a game-changer for cosmology, offering a new way to understand dark matter and the early universe. On the theoretical side, scientists have made strides in connecting black holes to quantum gravity, a field that tries to merge quantum mechanics with general relativity. One study published in 2025 proposed that black holes might act as quantum computers of sorts, storing and processing information in ways we don't yet fully understand. This ties into the famous black hole information paradox, which asks what happens to information that falls into a black hole. Does it disappear, or is it somehow preserved? These new models suggest that black holes might hold the key to unlocking the mysteries of quantum gravity, potentially leading to a unified theory of physics. And let's not forget the ongoing work with the Event Horizon Telescope. In 2025, the EHT has been refining its techniques, aiming to capture even clearer images of black holes like Sagittarius A and M87, with hopes of studying their magnetic fields and how they launch those powerful jets. Black holes aren't just fascinating because of their gravity. They also challenge our understanding of time and space in ways that sound like science fiction. One of the strangest effects happens near the event horizon, where gravity becomes so extreme that it warps time itself. This phenomenon, called time dilation, comes straight out of Einstein's general relativity. Imagine you're watching a friend approach a black hole while you stay far away. As they get closer to the event horizon, you'd see their clock start to tick slower and slower compared to yours. If they could somehow hover just outside the event horizon, time for them might crawl so slowly that a single second could feel like years to you. From their perspective, though, time would feel normal. It's all relative. This effect has been tested in less extreme scenarios, like with GPS satellites, which experience slight time dilation due to Earth's gravity. But near a black hole, it's on a whole other level. Black holes also inspire some wild theories about space. For example, some physicists think they might be connected to wormholes, hypothetical tunnels in space-time that could link distant parts of the universe or even lead to other universes entirely. The idea comes from solutions to Einstein's equations, which suggest that a black hole's singularity might connect to a white hole on the other side, spitting out matter in a mirror universe. While there's no direct evidence for wormholes, they've captured the imagination of scientists and sci-fi fans alike. Think of movies like Interstellar, which used real physics to depict a journey through a wormhole near a black hole. Another mind-bending concept is the idea of black holes as gateways to other dimensions. String theory, a candidate for a unified theory of physics, suggests the universe might have extra dimensions beyond the four we experience, 3 of space and 1 of time. Some models propose that black holes could interact with these hidden dimensions, potentially explaining mysteries like where Hawking radiation comes from or how information is preserved. These ideas are still speculative, but they show how black holes push the boundaries of our understanding of the universe. So, what's next for black hole research? The future is looking incredibly exciting, with new missions and technologies on the horizon that promise to deepen our understanding of these cosmic enigmas. One of the most anticipated projects is the Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s. LISA will be a space-based gravitational wave detector, consisting of 3 spacecraft forming a giant triangle with sides 2.5 million kilometers long. Unlike LIGO, which detects high-frequency waves from stellar mass black hole mergers, LISA will be sensitive to lower frequency waves, allowing it to detect mergers of supermassive black holes, the kind that happen when entire galaxies collide. This could give us a front-row seat to some of the most violent events in the universe, revealing how supermassive black holes grow and shape galaxies over cosmic time. On the imaging front, the Event Horizon Telescope is continuing to improve its capabilities. Scientists are working on adding more telescopes to the network and using higher frequencies to capture sharper images of black holes like M87 and Sagittarius A. One goal is to study the magnetic fields around black holes, which play a key role in launching those powerful jets we talked about earlier. Another is to capture movies of black holes, showing how their accretion disks change over time. These advancements could help us test theories of gravity and understand the physics near the event horizon. There's also a lot of theoretical work happening. Researchers are trying to solve the black hole information paradox, which we touched on earlier. If Hawking radiation causes black holes to evaporate, what happens to the information that fell into them? Some physicists think the answer might lie in holography, the idea that all the information inside a black hole is encoded on its event horizon, like a cosmic hologram. Others are exploring whether black holes could be linked to dark energy, the mysterious force driving the universe's accelerated expansion. And of course, there's the ultimate question. What's inside a black hole? The singularity, where density becomes infinite, breaks our current laws of physics. Could we one day develop a theory of quantum gravity to peer inside? The future of black hole research is bright, or perhaps I should say dark, and it's sure to bring even more mind-blowing discoveries. That brings us to the end of our deep dive into the fascinating world of black holes. We've covered so much ground today, from the basics of how black holes form to the incredible ways we detect them, like gravitational waves and X-ray emissions. We've explored the giants at the centers of galaxies, like Sagittarius A, and how they shape the universe around them. We've looked at the latest discoveries in 2025, from new gravitational wave signals to theories about primordial black holes and quantum gravity. We've also ventured into the mind-bending effects of black holes on time and space, from time dilation to the possibility of wormholes and extra dimensions. And finally, we've peeked into the future, with missions like LISA and advancements in imaging that promise to unlock even more secrets. Black holes are more than just cosmic oddities. They're windows into the fundamental laws of the universe, challenging everything we know about physics and inspiring us to keep exploring. I hope this journey has sparked your curiosity as much as it has mine. If you enjoyed this video, please give it a thumbs up. It really helps the channel grow. Share it with a friend who loves space as much as you do, and don't forget to hit that subscribe button to join the Cosmic Pulse community. We've got plenty more space adventures coming your way. So let's keep feeling the pulse of the universe together. Until next time, keep looking up.